introduction. So so today I'm going to talk about a topic. It's truncation by death. So I worked on this topic during my PhD thesis, and for a while I thought this topic was dying, but then obviously it looks like this is seems to be a very relevant problem that people are run into all the time, and a lot of people are thinking about this problem now actually. So so this is based on some very recent work. With my postdoc, Rachel Zhao at University of Toronto, and a wonderful collaborator, Matt Stenstrup at EPFL. So I will first give you a brief introduction of this truncation by death problem. So usually we have this treatment assignment Z, and for this talk, we just think of this treatment assignment as being randomized. Okay, and the real complication comes in when we have on the outcome side. So we have two outcomes. One is called intermediate outcome or intercurrent outcome, which is S, and one is the final outcome of interest, which is Y.
I think the mic is.
It's all right because we're using the room.
All right.
Okay.
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 Anyone on?
Yes, I think.
So most people can hear fine. One person cannot. So it's that issue.
Oh, okay.
Yeah.
If we want as well, if we want the screen to be bigger, we could minimize the chat for now as well.
We do want the screen to be big.
Yeah.
You want the screen to be bigger?
Let's just say that.
And you don't. Anyone know how to do that?
You press the little chat button and it will automatically shrink it.
It's a little chat.
So it's just grace.
Oh, I think it's.
There you go.
Yeah.
I couldn't see there's something else.
Okay. Is this the actual bigger? Oh. I think we'll just close the chat. But anyway. So we have two outcomes here, the intermediate outcome and our final outcome of interest Y. And the complication here is that Y is only well defined if the intermediate outcome S takes a certain value. So for example, S equals 1. Okay, so to make this more concrete, let's look at a particular example. So here we have a randomized trial for prostate cancer. And the treatment is chemotherapy, but you think of one of them being the active treatment. So I would just call it DE. So this is the chemotherapy regime that's supposed to improve survival. So it actually kills the cancer cells. And the control is more for symptom relief only. Okay, so it's not as invasive or as active treatment. So we have these two treatment assignment, and this is a randomized control trial. So this is the treatment assignment is randomized. And we're interested in knowing what's the treatment effect on quality of life for these cancer patients. So of course, there's this thing that we only talk about quality of life for people who are still alive. Okay, so if someone died, we don't talk about their quality of life. So here, Y, our outcome of interest, is only well defined if they survive. So the survival indicator S equals 1. So this is the kind of concept that we're looking at. So the particular data set we're working with come from Southwest Oncology Group trial. This was a phase 3 trial for some this late stage prostate cancer. We have about close to 500 patients aged between 47 and 80 years old. About half of them were assigned to active treatment, half of them assigned to control. And the data set, as in most of these oncology data trials, will have a longitudinal follow-up. So in this particular data set, we have a follow-up at 3 months, 6 months, and 12 months. And the primary outcome here is, of course, survival, right? We will run a cancer clinical trial. You want to see if this can improve patient survival. And this question can be sort of answered quite straightforwardly by just plotting what's the survival curve. So on the x-axis, we have the time since baseline, so 0, 3, 6, 12. This is the 3 follow-up time. And we have their survival probability by treatment groups. So the red one is the active treatment, and the greenish one is the control. Okay, so from this plot, you obviously see that the active treatment is beneficial for survival. Okay, so you can just eyeball this. But the next question is, how about quality of life, right? So the concern is that because this is the chemo, right? So this may influence people's quality of life. Okay, and so this is our secondary outcome in this trial, which is quality of life. And for this particular data set, this quality of life was evaluated through a combination of questionnaires. So the first part of the questionnaire is a generic quality of life questionnaire. And the second part is a particular prostate cancer module. So you combine these two to get a so-called global quality of life score that range from 0 to 100. And the outcome, what people are often looking at in these type of trials is the change from baseline quality of life. Okay, so so the difference between your current quality of life minus the baseline quality of life. And usually, this is just some rule of thumb for you to sort of get an idea of what this quality of life score will look like. So it's between 0 and 100. So a meaningful difference will be something like these 5 points. So this is the data structure of this study. So we have a binary treatment at the baseline, which we call Z. So we have 3 follow-ups here, 3 months, 6 months, and 12 months. At each follow-up, we first look at if the patient is still alive. Okay, so if they were alive, then we look at what's their change in quality of life at this particular time. So this is a longitudinal data set with about 3 time points. So if you look at the literature, we're not the first one to use this data set. Okay, so this data has been used quite extensively by people working in truncation by death. But if you look at all the analysis, you will find something pretty interesting that all of them only use the data at one particular time point, which is usually the last time point. Okay, so there must be some reason for that. I mean, these are all very high-profile papers published in very good journals, but they only use usually they only use the last data point. Okay, so so there must be a reason that why people only do that, and what we try to do today is to come up with a new framework that can leverage the full longitudinal trajectory, right? There's no reason that you have this longitudinal data set, but you throw away all the information in between, only use the last one. Okay, so by the way, if you have any questions, feel free to interrupt. I mean, this is mostly a conceptual talk. So the end product of this is an estimate. Okay, I'm not going to talk a lot about how I identify and estimate this parameter. Okay, so but it's just our new way of thinking about this problem. So before going there, let me first do a brief review of what people do for a single time point case. So where you only have a baseline and you only have one follow-up. In the data example, people often only use last follow-up. Okay. So again, this is our data structure. You have a treatment assignment, and our outcome Y is only well defined if S equals 1. So if you look at this problem, so first, when we see this problem, we see what people usually do in practice is they just take a naive estimate. Okay, so they do this estimate, which is the observed survivors in the treated arm. You take the average outcome minus the observed outcomes among observed survivors in the control arm. Okay, so this is the sort of the most intuitive thing that you can do, right? So outcome is not defined if S equal to 0, so you just throw this data away. But one thing that people realize, or at least most people in causal inference realize, is that this thing is not causally interpretable. Because people who survive under treatment is in general not the same as people who survive under control, right? Because here you're essentially conditioned on a post-treatment variable. So this is one way to understand this problem. So we divide the whole population into 4 different subgroups. Sometimes people call it straight up. So we have this LL group with people who would survive no matter what treatment they get. So these are people who are really healthy, right? No matter which treatment they get, they will always survive at least to 1 year after baseline. So LD will be patients who are saved by this treatment. So they would only survive under treatment, the active treatment, but would die under the control. Okay, so these are people who were actually saved, their lives were saved by the chemo. So DL will be patients who were killed by this active treatment. Okay, so they would survive under control so if they only take the placebo, but they will die if they took the active treatment. And the DD will be people who are doomed, so they will die regardless. Okay, so now from this perspective, we can see that. So the first part of this conditional set, people who survive under treatment, this will be a combination of the first two straight up, right? So this will be either you always survive or you only survive under treatment. These are the people who will survive under treatment. And the second subset will be people combination of L and DL. So you either always survive or you only survive under control. And these two groups of people, there's no reason to believe they are the same, right? And in particular, usually people who survive under control will be patients who are healthier to start with, because even if you just give them control, they can still survive. And the people who survive under treatment may, in general, on average, be weaker. So it's unfair to compare the same outcome among these two different groups of people. So this is where the selection bias comes from. Okay. All right, so what can we do instead, right? From the causal inference perspective, there has this so-called survival average causal effect. So you look at the comparison Y1 and Y0 in this always survival group. And why do we look at this group? Because we say Y is only defined if S equals 1. So which means the potential outcome Y1 is well defined if S1 equals 1. Okay, so your outcome under treatment is well defined only if you can survive under treatment. And then similarly, your Y0, your outcome under control is only well defined if you can survive under control. So your S0 equals 1. So in order for this Y1 minus Y0 to be meaningful, you need both S1 and S0 to be 1, right? So you need to be always survive regardless of when you take treatment or control so that we can make a comparison. Like, so another way to look at this is to take the intersection of these two sets. At least will give you the always survival. So this is the estimate that causal inference people have advocated. The first time it showed in the literature was in Robbins 1986. Of course, no one reads the Jamie's paper back then. Then Don Rubin made this popular again in this principal stratification framework. And then Julia Paul, who also sort of advocate for this. So this is one of the few examples where almost everyone in causal inference agree upon. There are not many of them, but this is one of them that, because it looks very convincing, right? This is the only thing that you can look at. If you want to compare Y1 and Y0, you need both of them to be well defined. And for both of them to be well defined, you need both of S1 and S0 to be 1. Okay, so in the causal inverse community, there's a consensus that we should look at this estimate. While after 30 or 40 years, if you go to practitioners and you ask them what they will do in practice, 99% of them will still do a naive estimate I just showed you in previous. And there is a reason for why people are still sticking to this naive estimate. The reason is that this causal estimate is, of course, causally interpretable. But there is a fundamental critique about this estimate in that this survival average causal effect is only defined for this so-called always survival. And what's interesting about this always survival group is we don't know who they are. Okay, so we know who survive under treatment. We know who survive under control, but there's no way for us to know if they would survive if they were given the other treatment option. Okay, so this is a fundamental problem with this estimate that we come up with an estimate that's causally interpretable, but many people think this is the wrong question to ask because it concerns about the subgroup that we don't know who they are. Nevertheless, I mean, we can still just apply this existing methods for SAYS. This is what I did for my PhD. We get a point estimate of 5.04. So this is just meaningful enough to say that the active treatment will actually improve the quality of life relative to control in this data set. And we can also estimate that this estimate will apply to 72% of the population, meaning that the overall survival group will account for 72% of the population, even though we don't know who they are. Okay, so what this tells you is that for a mysterious 72% of the population, we estimate this effect of 5.04. And this was almost 10 years ago, and no one is using it in practice. Okay, because 72% is not too bad, but the fundamental question is, who are these people? Now, we had this problem, but now we had a second problem is that now what if we have a longitudinal data? So the naive way or naive extension that you might think is, okay, since I know how to do this at 12 months, I know, then I can repeat the same thing for 6 months. Right? I just change my Y from being defined as 12 months to being defined as 6 months. I can repeat my analysis, I get my estimate. I can also repeat the same thing for 3 months. I can get another estimate for 6. Of course, you can do this, but there's one caveat here, that the subgroup that this estimate applies to changes over time. Because it's easier to survive at 3 months than to survive at 6 months, than to survive at 1 year. Okay, so the subgroup for people who, or the percentage of people who would always survive at month 3 would be more than percentage of people who would always survive at month 6, and finally at month 12. Okay, so you can come up with these 3 different estimates, but when you plot it, if you show a plot like this on the left-hand side, people will always try to compare these estimates over time and try to tell a story like how this treatment effect will change over time. But this is actually not right, because these treatment effects are for different group of people. So here comes the second critique, that even though I'm sure well, here a lot of experts in causal universe know we should not do this. But if you present this plot on the left to a practitioner, they will inevitably try to compare these causal effects over time. Any questions?
How are you estimating that quantity? Is it some sort of inverse probability weighting?
How do I estimate the size?
Yeah.
It's through some sort of instrumental variable like techniques. Yeah. All right. So this is the new framework that we propose, and we call this causal inference for all. And there are several meanings attached to it, right? So we propose a class of causal estimates for this problem. First, it applies to all time points. Okay, so this works for longitudinal data. And the second, perhaps more importantly, that this is the estimate that applies to all subjects. Okay, so remember the central critique about the SAYS is it only applies to a subgroup that's not identifiable, right? So now we try to solve this problem with this new framework. But of course, it's still causal estimate, right? So it's still causal interpretable. So hopefully this will appeal to researchers who may or may not like this idea of principal stratification. So how would I do that? So to explain the idea, I will just focus on this very simple example data, where data set we have 2 subjects. Okay, so the first subject, if they were given control, they will only survive to 6 months. If they were given treatment, they would survive to 12 months. And the second subject, no matter which treatment option they were given, they would always survive to the end of the study, which is 12 months. Okay, so this is our toy example data set where we only have 2 subjects. So recall that if we were to estimate SACE, then we'll only be looking at the effect for the second subject. Because if you only take if you only look at the 12 months data, then the second subject will be always survivor, and the first subject, this will be a saver, so they will only survive under treatment. So we will not, so their Y will not be defined. So now we want to define an estimate for everyone, right? So in particular, we also want to define an estimate for the first subject. So of course, we don't want to define the estimate at time 3 because this subject would have died by time 3. So instead, the closest thing that you can do is you pick the last time point before their death, which in this case will be 6. Okay, so now what we can do is instead of looking at a fixed time point and censor some subjects, for each subject, we look at the final time point before death or the last time point where they would always survive. Okay, so this gives us our first estimate, which is evaluated at the final time before death. So here in the so our estimate under treatment group little z will be evaluated at 6 months for the first subject, but 12 months for the second subject. Okay, you can already see that we have this is where we make this jump where we're able to define an estimate, right? Compared to the 6, right? This estimate is well defined for everyone in the population. And it's only possible to do this because we have this longitudinal data. Okay, so here, longitudinal data is actually helping us rather than creating problems or challenges for us. And in a lot of studies like this, we do have longitudinal data. Right? In a lot of studies with truncation by death, we don't just observe an outcome at the final time. We do have this intermediate outcome throughout the course. So this is why we can do this. I'm just going to show you the estimate, and you can see that with this change, when you extend this extend the treatment effect comparison from this particular subgroup to the whole population, the effect size shrink by almost a half. Which sort of tell you something. I mean, it's not quite significant, but the trend is tell you that you also get a smaller standard error because now you are looking at the whole population rather than looking at this particular subgroup. Okay, but of course this is not ideal because first of all, it's not using the full outcome trajectory over the time course. It's only using the last time point. And also, in some sense, this estimate will unduly favor the treatment that improves survival. So what I mean by that is if you look at the first subject, right? So here we look at the comparison at 6 months. So we know that if they were given control, they would die right or shortly after 6 months. Because we know from this is the oracle data, right? We know that the subject will not be able to survive to 12 months. So chances are that this Y1 6 months 0 is pretty bad. Because this is something that's measured right before death. And in comparison, this Y1 6 month 1 is probably going to be okay. Because this subject is going to survive for another 6 months. At least, right? So if we only look at the last time point, then usually for the treatment that improves survival, so in this case, treatment 1, their outcome will be pretty okay. And for the other treatment, then their outcome will be most likely to be pretty bad. Yes.
In a real world longitudinal setting, how could you know that one subject will, well, the results of a subject in either treatment cases? Because surely you can only give them one type of treatment.
Right, you would, and this is the Oracle data, like you will never be able to see this. Now I'm just talking about how, if you had this data, how would you define a treatment effect? I haven't talked about how do I use the actual data to estimate it. That's a different problem. But I think this is the first step that we need to clarify, right? Because if we first talk about our estimate before we talk about how to estimate it.
Just because you said this allows you to use the whole population,
Mhm.
does that include the DD group where they would have died in either outcome at 12 months? Because this seems like it requires either LL, LD, or DL.
Great question. So the DD will depends on time.
Yeah.
There might be DD, well, we are all DD in 100 years. Right, but this will require you to be LL
Yeah.
at some point throughout this course, and you are looking at the last time point, so that they are LL
Oh, okay. So it's the last time point on each
for each
track,
subject.
which
Yeah,
then, okay, it's not just the current time point of 12 months.
right,
Okay.
exactly.
Just
We are all, so the assumption is we are all LL at some point. But of course, we're all DD eventually. Okay. Okay, all right. So this is this was our first proposal, and the critique here is maybe this will unduly favor the treatment that improves survival, right? So our next proposal here, I think it's sort of quite obvious, is instead of taking the last time point, you take an average across this the whole course, right? So for example, here for the first subject, this subject will be LL until time 2. So instead of only taking their measurement in time 2, we take an average of their measurements from baseline to time 2. Okay, this is sort of a very intuitive thing to do. And then for the second subject, this subject will be LL until time 3. So we take an average of their outcome until time 3. So of course, there's a caveat here, like for different subjects, you are taking an average across different period of time, but each subject will receive the same weight. Okay, so here, even though the second subject survives longer, we still assign the same weight to a second subject as to the first subject. And this is what we get. You can see that now with this average scheme, the effect almost go away. Okay, it becomes almost negligible, right? So I think this is also one of the things that you can get from this scheme where you can sort of fully leverage the longitudinal data. Because previously, so what happens if you think about this application, what would likely happen is that when you first have the chemo, right? So your quality of life will probably first drop right after the therapy, yeah, because of the side effects. But if the surgery is working, then because the tumor cells were gone, then your quality of life will back up. Right, so this is, if you only look at the last time point, then if eventually you only look at the last time point, then the active treatment will increase your quality of life. But if you look at the whole period, then maybe the effect's not so significant. And in this case, it tells you that if you look at the whole period average out, then the effect almost goes away. Okay. Also, I mean, this is great, but I mean, there's still a minor critique that usually in this kind of studies, well, these visits are not evenly spaced over time, right? Usually when you have a chemo, you first, right after the surgery, you will have more frequent visits. And then after that, you may go back, if you are still alive, you don't go back as often as initially right after the surgery. Okay, so as you can see from this data set, right, initially you go back every 3 months, then you go back every half a year. So naive average may put too much weight on early time points. So we can do something like AUC adjustments. So suppose that this is your underlying quality of life curve. So you can sort of, and these are the three measurements you have. You can sort of estimate the area under the curve, where you can take into account that if this is a longer time period, then you don't just apply a naive average. You take into account of the space between the visit times. Okay, so this is the minor adjustment. It doesn't really change the conclusion here. So the point estimate is still very small, meaning that if you average over this time period, then you essentially don't get any meaningful improvement in quality of life. Right. So this is just our summary so far. So this is how we would propose to approach this kind of problem. So of course, the primary analysis will always be survival benefit, right? So these are the two survival curves. So under treatment Z, let's say you survive to this point, TZ, and under treatment 1 minus Z, you survive to T1 minus Z. And the difference between them will be the survival benefit. So how many months or how many years do you survive? Actual years you get under treatment Z. But then we can report different, we can look at the effect of a change in quality of life. So we can do this by two parts. So first time period, so between these two dashed lines, we call this guaranteed survival times or always survival time. So you would always survive regardless of which treatment you are given. Okay. So within this time period, the individuals will survive under both treatments. So we can compare their weighted potential outcomes during this so-called guaranteed survival period. Okay, so and here, I mean, this is just a mathematical form for what we for the while guaranteed survival estimate. So you can take a weighted average of your observations within this time period, and this ways you can choose it to suit your scientific goals. Like for example, if you want to just look at the last time point before they died, you can choose the weight to be 1 at the last time point and the 0 otherwise. Or if you want to look at average, you can set the weight to be 1 over t. Or you can, sometimes people may want to look at cumulative. You may not want to do this for quality of life, but let's say if this is if the outcome y here is expenditure or cost, then it actually matters, right? You are interested in the cumulative cost over time, or you can have an AUC base. So this ways can be, you can choose these ways to depend on what question you want to answer. But the point here is you are comparing treatment group 0 and 1 within the same time period. Okay, within the same guaranteed survival period. So there's no selection bias. So this is a causal estimate. Okay. And then we have some additional data that we haven't used so far, right? So for the first time period, we can we have both y1 and y0. We say we compare, we try to estimate treatment effect, weighted treatment effect in that period. For the extended survival period, where you would only survive under treatment Z, but not under treatment 1 minus Z, you can also report something called wild extended survival. So what's the additional quality of life you gain in this period? And in this period, you don't get a causal effect, right? Because here you only have YZ, but you don't have 1 minus Z. And so you only have your YZ defined in one of the treatment arm. But then you can report what's my quality of life in this additional years that I will survive under the active treatment. And usually cumulative, you can do AUC. This is our estimate. Okay, now I will very briefly talk about how we identify this new estimate. The first estimate we talk about is in the first period with well guaranteed survival. So you can see that the time is from I equals 0 from baseline to the minimum of T0 and T1. So during this period, you will survive either under treatment or control. And we can rewrite this. This is just a mathematical reformulation. We can take the randomness out of the weights. So we can write this as a fixed weight. So you can see that, and this is very simple conditional expectation. So you can decompose this as three parts. The first part is a given weight. So this is, the investigator chose the weight. So these are constants. The last piece here is the probability of the so-called principal strata. Okay, in identification, we still go back to principal strata, and in fact, there's an interesting fact that if you choose the weight in a particular way, then you can get back the survival average causal effect. But that weight is not very intuitive. Like no one would even, no one would think of that weight in the first place. But mathematically, you can choose a weight in a way such that you get back the survival average causal effect. But for any usual weight, this will be different. So yeah, so eventually, so the point here is our identification is not very different from our identification in the survival average causal effect, because really what's missing here, or this proportion of the principal stratum will be identified under the monotonicity assumption, which people often assume for survival average causal effect identification. And what's the last piece here will be what's the mean potential outcome in this particular principal stratum. And I said I'm happy to go into more details if people are interested. But essentially, the high-level ideas we can identify this estimate in a very similar way to the survival average causal effect, where the survival average causal effect is essentially here we look at if your minimal survival time equals T. And the survival average causal effect say you will always survive at time T, which means your minimal survival time will be greater or equal to T. So this is a subtle difference. So they are not exactly the same, but they can be identified in a very similar way. And in particular, one of the approaches is we use a so-called substitution variable, which is like an instrumental variable for the always survive for the principal stratum. This is an old paper that I wrote for my thesis. But in principle, you can maybe adapt other methods for identifying the survival average causal effect to this estimate. So the second part of the story is the so-called is the outcome in the extended survival period. Okay, so or if you look at this plot, this will be the area under curve during this additional time period. So if a subject will survive up to time 12 under treatment, but only survive up to time 6 under control. So this is from 6 to 12 is a period where you only have YT1, but you don't have YT0. Right? So for this period, we can only report what's your average YT1 among during this period. So this is mu extent. So this is our second estimate. And the identification of the second estimate is actually quite easy, or almost come for free, because of the simple decomposition over here. So the blue part is the mean potential outcome and the treatment in the first time period, which we already identify in the when we identify the first estimate. And the sum of these two will be what's the quality of life among the observed survivors in the treated arm, so lambda 1 here. And this is what we can identify almost trivially via the math trial. Right? So if you so the red part will just be the difference between the green part and the blue part. So if you really want to see some equations, the whole green part will just be a weighted average of listing, and this is just observed outcomes among survivors. And the minus mu1 is what we already identified in the first phase when we try to do that causal comparison. Okay, so and finally, coming back to this data application, to show you, and just to summarize and to give you a sense of story here. So again, we have a baseline, we have a binary treatment, z equals 1 if this is a chemo that actually prolongs survival, and z equals 0, it will be some sort of placebo treatment with a bunch of baseline covariates. And the sort of instrumental-like thing we use is the baseline quality of life. And this is a summary of all the estimates that you would get. If you only look at the SAYS at 12 months, you would get an estimate that's a little bit larger than 5, which suggests that the treatment seems to have a pretty significant effect, a positive effect on quality of life. But remember, this is only applicable to the overall survivor at 12 months, which is the non-identifiable subgroup. Okay, and the next three will all be our marginal estimates, measured at different time points. This is if you only take the measurement, or if you only care about how they behave when they exit the study. So you can see that there's a significant decrease in the effect size that we estimate. And if you actually look at the average, you can see that this effect almost go completely. And we can also look at what's the estimate in the extended survival period, right? So first, we recall that there's an increase in restricted 1-year survival time under the treatment relative to control. And in this study, the treatment has an effect, but not very significant, 0.05 years, which translates to less than a month. And this is the list estimate 0.43 is the cumulative quality of life within this period, a cumulative Y within this period. But here Y is changed from baseline. So after we add it back, this is the cumulative quality of life within this 0.05 years. Okay, I think that's it. So in this framework is called causal inference for all. There are some two important extensions. One is we extend the original space estimate from a single time point to all time points. Right? Our estimates will leverage the data using all the measurements across in the longitudinal trajectory. And I think what's more importantly is with this longitudinal data, we now are able to define an estimate that applies to all the subjects rather than an unknown subgroup. This comes with a caveat or a cost that for different subjects, we define this over different time span. Right? Because for each subject, we define this from 0 to their minimum survival time. So the minimum of TI1 and the TI0. And this time span can be different from different subjects. And usually this is not identified for each individual subject. Okay, so we still have some non-identifiable component. So you can think of this as a way to convert that non-identifiable component to who this estimate applies to which time period this estimate applies to. And we think this is more, this is easier to sell because at least now no one can complain that they are left out of the analysis. Which I think is important for many reasons. And for each patient that comes in, we can tell you first, under this active treatment, this is how many, on average, right? This is how many years you would live actually, right? So in this particular case, it's 0.05 years, but we can tell you how many additional time you can live. then I can tell you that in the time period where you would always survive, what's your average change in quality of life? Then in the additional time you would survive, what's your expected quality of life within that period? We can't tell you what these periods are. That's a caveat. But we can tell you that within this period, what's the quality of life? So there's still some non-identifiable component, and I think this makes sense because this, I mean, something has to be non-identifiable here because we're dealing with this truncation by death. If we want to stick to a causal interpretation, actually, if you don't care about causal interpretation, so let me just mention one thing. If you don't care about causal interpretation, people have used the thing called while alive estimate. Okay, so you can do a comparison. You can compare this lambda 1 here versus the lambda 0, which is the period until time 6. So you can compare these two. The while alive estimate will correspond to different time periods under treatment or under control. Right. So here, you can think of what we do is we decompose this while alive estimate into two parts. The first part is the causal part, and the second part is nothing to compare, but you still report the estimate. Okay. And the last this framework, I mean, this idea is quite general. So in the paper, we also do this for the so-called conditional separable effects, which is a framework developed by Thomas Richardson, Jimmy Robbins, Matt Stenshot, and a lot of people who they have their own view of how we should define estimates in this truncation by death problem, but also as a conditional estimate. So I would just mention that this idea can be also used to convert their conditional estimates to a marginal estimate. So it's not specific to states, but it's more general than that. Okay, I think I will stop here. Thank you very much.
Okay, does anyone have any questions? What time? Bit of time.
The quality of life, you're just using scores rather than something like qualies.
No, really.
So quality adjusted life years.
Oh, yes.
It occurs to me that this follow-up time, like if someone does survive and they just get better, and then you had also one at like 2 years and 5 years, because it's a weighted estimate, the longer you kept the follow-up time, the less relevant that score then becomes over time, as it were, if they do recover. Would something like integrating time into the metric distort this way of estimating things, or does it only work for like unitless outcomes?
No, actually in this one, you mean I guess you are talking about second period where they only survive under one treatment.
Yeah.
Then you can look at the cumulative. Then of course, the longer you live, the higher the quality of life would be. But of course, so you should interpret that cumulative in the context of the length of the time.
Yes.
Right. So I can tell you on average, you are going to live 2 years longer. And within these 2 years, this is your cumulative quality of life. And so I guess these two go together.
Yeah, a cumulative outcome there, which is like scale to 1, like if you had a really bad 3 months, it would almost get removed by that cumulative one, because it's only ever getting closer to 1 over time. I was just trying to wonder if there's a way to then get the time units within an outcome as well.
Yeah. Like if you can assign different weights, right? This is a weighted sum. I mean, if you really want to discount that initial period, you can assign a smaller weight to that.
Okay. Cheers.
Right. Yes. I mean, this is the way it is, right?